So Bell's theorem doesn't prove that EPR experiments can't be explained without non-locality. Bell's theorem proves that you can't explain EPR experiments, period, in a forward wave theory. So barring the possibility of any third theory in addition to the reverse wave theory, Bell's theorem, by refuting the forward wave theory, it really constitutes another proof that the waves move in reverse. Now, let me just spend a few minutes. I'm sorry, because this is really the most interesting part of my talk. I can stay as long as you want, but I'm sure some of you have to leave. What do we have here? We have a theory which says that all particle motion occurs by following a wave coming from the detector. Now let's apply this for a minute to light. Light consists of particle photons coming toward the observer, following a wave coming from the observer. And the wave determines the dynamics of those particles. In particular, the wave determines the velocity of those particles. So the frame of the observer determines the velocity of the particle photons. This immediately explains the basic fact on which special relativity is based. Light always moves with velocity c relative to the observer. Now, this is not to say that whenever I see light from any object, no matter how far away it is, that it's making its entire trip following a wave coming from me. That would clearly be absurd. I wasn't even around when the light was emitted from some distant astronomical object. What the reverse wave theory establishes is the validity of a Lorentz transformation over short distances. But that's exactly where we define our units. Our basic units have to be directly perceivable magnitudes. And then you relate those directly perceivable things to larger and smaller things that you can't directly perceive. Now, we know that in a Lorentzian universe, an object moving at velocity c relative to one observer will move at velocity c relative to all observers. So even if a photon is coming from a distant astronomical object and switching waves repeatedly as it travels, it'll always be moving at velocity c relative to me. So it'll get here in the time predicted by current relativity theory. Now, the fact that relativity theory involves reverse waves shouldn't really come as a surprise. The current interpretation of the Lorentz transformation says that if I'm first standing still and I then move, the fact of my motion makes every object in the universe to its farthest reaches suddenly change size. Talk about a non-local theory. The only way my motion could possibly affect the apparent size of any object is if the motion affects the light with which I observe the object. And given that it's specifically the velocity of the light that's so affected, the only way this could happen is if something's traveling from me to affect the velocity of the photons. So one could actually come to a reverse wave theory just by considering special relativity. Now, it might appear that what I'm offering you here is a Galilean explanation of relativity. And in fact, most attempts to explain relativity amount to trying to do that. They want to reduce it to Galilean space-time. That's not what this theory accomplishes. What this theory accomplishes is to explain why we live in a Lorentzian universe, and to explain it in terms of the physical attributes of light. Now, to illustrate this, I'd like to look at the next slide. A simple example. An observer sits at a midpoint between two lamps. The lamps flash at the same instant of time. The light travels at velocity c relative to an observer here because they're following a wave coming from him. So he'll see both flashes at the same instant of time. But now consider a spaceship moving rapidly from left to right and an observer in the spaceship. The photons he will see, if this observer could see the photons that he sees, they'd be moving at velocity c plus v, where v is the velocity of the spaceship. And the ones from the other side would be velocity c minus v. So if the spaceship got here at the same instant that these photons caught up with it, the ones from the other side wouldn't be there yet. And the guy in the spaceship would see the two lamps flashing at different times, even if he makes allowance for the time of flight of the photons. So even if you try to understand this with a Galilean framework, you end up being forced to recognize that it's really Lorentzian. If simultaneity is relative, as this example illustrates, then apparent lengths have to be too, because by the length of a moving object, you mean the distance between the 2 points, endpoints, observed simultaneously. And if simultaneity changes, the apparent length will change. Now, in fact, you can use an example exactly like this to derive the Lorentz transformation, just like in ordinary textbooks. Now, our concepts of space and time are formed by observing real objects and their motion. We form the concept of space by observing an object can move and another one can take its place. We form the concept of time by observing motion, and it can occur at different rates. Time is a measure of motion, as Aristotle put it. But all of this observation is carried out using light. So, and light is of this reverse wave following nature. So this effect is built right into our very concepts of space and time from the beginning. But when an object appears to be shorter when it moves, or when an object clock appears to turn more slowly, the object itself hasn't changed at all. All that has changed is the light that you use to observe the object. The object merely appears to change. Consider, for example, the length as observed in the rest frame, or frame stationary to us. If that object now moves, and you want to measure the very same physical attribute of the object, you'd have to look at the two ends at non-simultaneous times because of this effect. But this effect is produced only due to a change in the light, due to the motion. Now, in order to see the same physical attribute of the moving object, you have to remove the effect of the changed light. And the way you do that is with a Lorentz transformation. This is exactly what you get in relativity theory. Let's see now. In other words, the light is what gives you the Lorentzian effect, so you have to do a Lorentz transformation if you want to get the very same physical attribute of the object. And sure enough, if you do a Lorentz transformation, the interval in one frame transforms into an equal interval in another frame. The mix of time and space is going to be different, but you get the same quantitative result. And the only reason the mix of time and space appears to be different is because of this effect on the light. This is why all physical laws have to be covariant. If you transform to a new frame, all of the transformed quantities actually represent the same physical attribute of the objects. So, of course, the laws have to remain the same. So what we have here is an objective relativity theory. Objects are actually the same to all observers. They only appear different because of the change to the light. It's just as if one observer had red-tinted glasses and another one green-tinted glasses. They appear different, but if you remove the effect of the difference in light, they're both seeing the same thing. Now, when quantum mechanics was made relativistic, all kinds of useful results fell into place. And physicists concluded that there's a special intimacy between relativity and quantum mechanics. In fact, it's more than just an intimacy. Relativity and reverse wave quantum theory are actually one and the same theory. If Einstein hadn't yet discovered relativity theory, the reverse wave theory would have predicted it.